sensor manufacturing company, which is quite expressive because it shows us a beautiful city with lots of sensor infrastructures on top of which we have different services running. So the important thing to notice about this is not just a vision, actually. A bunch of these services are already running in different places in the world. And typically when we talk about smart cities, the scenarios that people go back and forth about are smart street lighting, waste management, smart parking spaces. For instance, there's a network company that a couple of months ago deployed 12,000 sensors in Moscow to regulate the parking spaces over there. So they are managing the parking availability of parking lots, and this way they resolve the big traffic congestion problem over there. So lots of these things are already running. We have also lots of air pollution tracking applications, and also everything that is related to structural health, such as the state of buildings and bridges, is also a common use case. So when we take a look at these infrastructures, we can observe a few characteristics that are going to be recurring. They're typically deployed outdoors most of the time. They're going to deliver data in various ways. They can deliver data periodically in an event-driven fashion. And they are going to produce a massive amount of data because there's lots of them everywhere. And if they're going to send data periodically, it's going to be a huge amount of data to process. And in the end, they are going to use different network protocols and network standards such as Sigfox to push data to applications. So there's lots of effort that has been done at the level of devices, sensors, network protocols, routing algorithms, energy efficiency, but there are few efforts that have been done at the level of the development of services that run on top of these infrastructures. So we were asking ourselves, we were lucky enough to work with people that are actually sensor manufacturers or network operators in this domain. So we started to ask ourselves, how can we leverage all these infrastructures to develop some kind of a service on top of that? And what would be a good approach to do that? So we were having some kind of a knowledge when it comes to small-scale environments. Typically what we call that is pervasive computing, cyber-physical systems. So we had a good approach that was targeted to development of these kind of systems. And what we wanted to do, we wanted to get somewhere over there to do actually an approach that would fit for large-scale orchestration. So we started by identifying challenges. So the first one was service discovery. So what happens over there is that in a small-scale environment, typically when you enter in a room, you have your tablet and you would like to print out a document or seamlessly display a presentation on a screen. So the service discovery mechanism is going to find some kind of a device which is capable to do that for you. When it comes to large-scale orchestration, most of the time the manufacturers told us that it doesn't make sense to them to discover individual sensors, but they prefer to discover some kind of an object of interest. So let's say we have parking spaces, so they prefer to discover parking lots. So some kind of an object of interest that is more easy to handle for them at the application level. The other challenge that is going to pop up is the data gathering problem. At a small scale, what we're going to have is an event-driven interaction. For instance, something occurs in the environment, the data is going to be pushed to the application, or a query-driven interaction that when we need this data, we're going to look for the sensor, we're going to look for the temperature, we're going to get it. Most of the time, sensor manufacturers, they were asking us to give them some kind of a way to express the periodicity of the delivery. This was an important problem to them, and they wanted some kind of an application-specific concept that would allow them to express that. Another problem that is going to come up when we scale up is data processing, and this is basically going to happen because people that are working on big data are realizing that the sensor infrastructures are producing enormous amounts of data, and actually HP had a report which said that in 2020 the number one source of big data is going to be Internet of Things. So it's really a problem, and it should be addressed at the application level as well. Well, and the last challenge is actuating, which is not really a large-scale orchestration challenge, because it appears perfectly well as well here. At a certain moment of time, you want to actuate something, to display some kind of a message, notify people, and this and that. So this is not really a large-scale orchestration challenge, because there are a few moments where you really want to actuate hundreds of thousands of devices at one moment in a time, right? But we need to address this, because it's a part of the global picture. If we would say that we would stop at data processing, what happens when I want to actuate something? So it's a part of the whole picture, but we're not going to spend more time addressing this issue right now. So if we get into service discovery, we are going to identify three requirements. The first one is large scale. This means that these sensor infrastructures are usually evolving. If we have, for instance, smart parkings in a city, we have 10,000 sensors, such as in Moscow. Maybe in a couple of months, we're going to have 20,000, which means that the service discovery mechanism has to evolve with the infrastructure. So, in a way, this service discovery mechanism has to be evolvable, and it has to abstract over the masses of sensors that is involved actually in the infrastructure. The other requirement is about infrastructure features. As I already mentioned, it makes more sense to reason when it comes to large-scale orchestration. It makes more sense to reason about objects of interest that are going to encompass sensors, that are going to comprise a whole bunch of sensors. So this is also something that needs to be done when it comes to a service discovery mechanism for this problem. And the last requirement is quality of service. I mean, when it comes to real-size deployments, with hundreds of thousands of sensors, there's a big probability that you're going to have a few sensors going to fail, or maybe many sensors going to fail, that are going to misbehave. And you basically don't want your application to crash if it happens. So as well, there is this requirement, which means that the service discovery mechanism has to abstract over individual sensor failures. So we need to, it's not that we're going to ignore them, but the application has to work without any problems, even if there are failures, sensor failures. So if we talk about data gathering, there are several ways how sensors would interact with services, with applications. We basically inspired ourselves of the work that has been done by Samir Tilak. He proposed a taxonomy of viral sensor network models, which describe how sensor can interact with applications. So the first model is the periodic one, which is great for tracking applications, tracking the position of cars. The other one is event-driven, which is basically the one you would find anywhere when you're, for instance, having a motion sensor and someone gets into the room. There's some kind of an event that occurs in the environment. You push the data to the application. The other one is query-driven, which means that you would like to go pull the data from the sensor to identify the temperature in the room. And the last one, the hybrid one, is just a combination of the first three ones, which means that it can be some kind of a complex object which can sense different types of data, and it can have different ways to interact with the service on the top. So this is also what is a part of this is the requirements on data gathering. And what we did is we wanted to take all these application-specific concepts, and we wanted to map them into the network infrastructure. So we asked ourselves how we're going to do that. So what we did was we introduced a domain-specific design language, which is called DiaSwarm. And this design language revolves around the paradigm which is called Sense, Compute, Control. Well, this paradigm has been introduced by Taylor in his book Software Architectures. And this is a paradigm that is dedicated to applications that are interacting with an external environment. It is very, very simple. It has only 3 components. And that is actually its power, because it's so minimal, so it's so easy to express things in it. So the first component is a device, which is basically going to sense data from the environment. The context component is going to transform data, aggregate, filter them, and produce something more interesting, some kind of a context data. And the controller, in the end, is going to trigger an order if it's necessary to actuate actually something and to have an impact on the environment. So that's how it works. Well, here we have an example of an application design in DiaSwarm. So on the right side, you have the graphical illustration, which is actually, as you can see, the design take the form of a directed acyclic graph, which starts from sensors and goes up to actuators and passes through context and controller components. So if you would like to declare a context, that is how we would do that. The 3 lines under the context keyword specify an interaction contract. So this is the way the device is going to be interacting with the context. The first line specifies the data gathering model. So in this case, it's periodic, and it has to happen every 10 minutes. So sensors are supposed to deliver data to the context every 10 minutes, and the computation is going to happen every 10 minutes. The second line refers to the service discovery mechanism, which means that sensors have to be grouped by parking lot. And the last line specifies how the context is supposed to interact with the remaining components, with the subscribed components in the application. So in this case, every time the context is going to compute a new value, the result is going to publish to subscribed components. The controller is a bit simple, but the idea is the same. It defines one interaction contract, which says that when I'm going to receive the value from parking availability, then I'm going to trigger the update action at the entrance panel. So this is basically the design specification, design declaration. And what we're going to do with this, we're going to actually take this and feed it to a compiler and generate a dedicated programming framework. So currently, we generate programming frameworks in the Java programming language. And the great thing about it is that we can enforce actually all these application-specific concepts that we declared previously in the framework, which means that the developer doesn't need to handle any more service discovery problems, data gathering, and the computation is going to happen at the precise moment that he declared at the design time. So he's going to have some kind of a framework that is going to guide him. He's only going to have to fill in the placeholders. So there are some free spaces where he has to introduce the application logic. And that's basically his job. So most of the thing is going to be done already by the compiler and is going to be already introduced in the framework. As this is the same thing. This is also the case for interaction between components. So this is already handled by the framework. So just a few words on the future work. We're currently working on data processing. This is actually something that I didn't address yet. What we're working on is we're trying to understand if there is a way that application design can influence the way data are processed. So if we're dealing with big data, we can have three different strategies that we can work with. We can work with batches, micro batches, or we can do streaming. So actually what we did right now, we just handled the batch processing strategy, which means that we give to the developer at design time some kind of a high-level design construct, for instance, a MapReduce paradigm. He's going to express how the computation should happen, and we're going to generate a bunch of code in some kind of a backend. So for this example, it's going to be code in Hadoop. So the developer doesn't need to handle actual data processing at the implementation phase, but this is already done for him. He just needs to fill in the application code. So another topic that we're going to address is network infrastructure independence. And what we basically want to do is we want to take the object interactions and map them into the API of the target network. So there are not many standards. I mean, the networks that are there that allow us to interact with sensors are heterogeneous and they don't follow the same rules. So, for instance, we're working with Sigfox, and in the beginning of their technology, they were having a great uplink, so we could collect data, but they didn't have any downlink, so we couldn't actuate anything. So, basically, we had to introduce different network standards and different protocols, and in the end, we realized that it would be quite good to have a few informations introduced at the design time, then generate some kind of a code which is going to handle this and is going to actually map these requirements on the network. So this is the other topic we're working on right now. And to conclude, we propose a domain-specific approach to developing applications for massive sensors. And what we presented are design abstractions that are going to allow us to express several things, such as the service discovery, component interaction. We proposed also a few service discovery models and data gathering models. Thank you very much for your attention.